Okay, so we are going to finish up the practice problems we need to do in Module 3. And I've already have the very last problem that we're going to be doing pulled up on the screen here. And this is on page 42. This is sample problem 2.6. So we'll read through the practice problem here. We'll go through it, and then we will be all set to start working on the application problems. Okay, so what we have here is it says we have for a new sailboat, a designer wants to determine the drag force that may be expected at a given speed. To do so, she places a model of the proposed hull, and that's what you see here, this kind of brownish section here, in a test channel and uses 3 cables to keep its bow on the center line of the channel. So that's right down the middle here. A dynamometer readings indicate that at a given speed, the tension in the channel, or I'm sorry, the tension is 40 pounds on cable AB. So AB is right here. So 40 pounds on that cable, 60 pounds on cable AE, which is going vertically. They want you to determine the drag force exerted on the hull and what is the tension in AC along here. Okay. Now I'm just looking, they are giving us, does it ask us for the angles? Does it tell us what the angles are? I'm looking. Oh, I see. They don't give us the angles alpha and beta, but they are giving us the distances. So we'll be able to figure those out, okay, even though they're not explicitly given to us. So what we want to do is, number one, let's draw a free body diagram of what we have and what we need to find. And I think we'll get a good indicator of how we're going to approach this. As you can imagine, we're going to be using that rectangular component method that we've been practicing here in Module 3. So this is sample problem 2.6, okay? And right at the top here, at the beginning of every one of our problems, we are going to add our convention in the upper right-hand corner, okay? So we know that all the forces that are going up and to the right are going to be positive. Anything going down and to the left are going to be negative. So what I want to do here is I'm going to start again. Remember, we are using half of our sheet of paper, okay? A third to a half. So nice big diagrams here, because remember, we have to add angles and labels and arrowheads, and otherwise it gets so cluttered to add all of that stuff. So we want to give ourselves enough room. So as we look here, we want to put tension forces along each one of the cables here. So we're going to have one going vertically down to point E, up to point B, and then up to point C as well. So what I'm going to do is we are going to kind of draw these. Okay, this is going to be, I'm going to call this one TAC. So tension in cable AC. Then we've got the tension in AB, and we know this one to be 40 pounds. So TAB is going to be equal to 40 pounds. Okay. And then we know that we have a force going straight down, and in the problem, it told us that this was 60 pounds going straight down. That was the tension in AE. Okay. Now, they want us to also determine what is the drag force. So each one of these forces represents the tension in each one of the cable, but there's a drag force that we have to determine on that hull. Now, since the flow is going to the right, our drag force is going to also go to the right. So this is going to be FD. Okay. So drag force is what I just used for that. Now, we need to, as you can imagine, we've got 2 forces that are not on the X and Y axis. We're anticipating we're going to be using our rectangular component method. So that means that we have to find the X and Y components, okay? So part of that is going to be what are the angles? So before we can do any sines and cosines, we have to know what the angles are. So we are going to calculate this angle here, okay? And I'm going to call, I know that they have beta and alpha in those two positions, but if we use kind of that standard position adjacent to the horizontal, then we can use, if you would, the cosine function for our x's and the sines for the y's, which is what we see most often, okay? It really doesn't matter which angle we get, but I like using those. So I'm going to call this one theta, okay? And then we are going to use the angle over on the other side over here, again, adjacent to the horizontal. And this one we'll call phi. So I'm going to use the little p because alpha and beta are used in the problem. So we'll use theta and phi. All right. So now what we want to do is we want to simply determine, what those are. So if we look back at the illustration that we have here, I'm going to do phi first, okay? You'll notice that we have a distance over of 7 feet and then a distance down of 4 feet, okay, from where they are attached. So for phi, we would use the tangent of phi is going to be equal to the side opposite, which would be our 4 feet divided by, oopsie, I'm so sorry, I'm not on the screen, divided by the 7 feet, okay? Feet cancel as far as units, and then determining or using that tangent function, and depending on your calculator, it might be an atan or an inverse tan. What do we get for the angle? 29.72, is that what you said? That sounds good. So 29.72 degrees, okay, and that would be angle phi. So I'm going to put my little cloud around that, okay. And then theta, all right, theta is the angle here. So if we go back to our illustration, okay, and we look at the dimensions that were given, theta is going to be right here. So we would have 4 feet down again, okay, and then they have 1.5 feet over. Okay, so if we look here where theta would be, the side opposite would be the 4 feet, and the side adjacent would be the 1.5. So over here, I'm going to say tangent theta is equal to 4 feet divided by 1.5 feet. What do we get for theta? So you should have your calculators out, punching it in, making sure we're all getting the same answer. 69.4 degrees. I think that sounds right. Yep. That's what I have. 69.4. Okay. 69.44. Okay. Yeah. We'll pull another decimal place. I like it, Lacey. That way we have 2 for each one. Okay. So that really completes our diagram. Well, no, it doesn't. Well, it does. It does. It completes our diagram because then we're going to be doing components. So number 1 is diagram with convention, right? So now what we want to do, step number 2, because now we know our angles, we are going to calculate the components, right? So go ahead and draw the components for the 2 forces here. Just draw the vectors for them on our diagram. And then make sure that you label them appropriately as well. So you should have an additional four forces on your diagram. You should have a TACX going to the right along the x-axis, TACY going up along the y-axis, TABY again going up along on the y-axis, and then TABX going to the left on the x-axis. Okay. Now what we need to do is we need to calculate each one of those components. Okay. So down here, we are going to write those out. So I'm going to start with TAB. All right. So the X component of TAB, which is right here, if we use the angle that we have phi, which is 29.72 degrees, okay? So if we look at that angle, that is going to be the cosine of that angle when we put it and use the hypotenuse of 40 degrees. So TABX is going to be equal to the cosine of 29.72 degrees times 40 pounds. Okay, make sure you put your units in there. And then what we'll do is we'll multiply that out and we'll get a value for TABX. Let me know what you get for that value. I got 34.75. Does that sound right? 34.73. Now I gotta do it. 73 as well. Okay, so 29.72. Whoopsie. Might be because I only had one decimal place on mine. Okay. So 34.73. Okay. And that's going to be pounds. So I'm just going to put a line underneath here, or you could put a nice little cloud as an intermittent answer. Remember, final answers get a circle or a box. Okay. Now for the y component, okay, if we look at that very same angle, TABY would be equivalent to the side opposite. And we're going to use the hypotenuse, so that would be using the sine function. So TAY is equal to sine of 29.72 degrees times 40 pounds. TABY. I'm going to push this up a little bit. What do we get for that one? 19.84. Anybody else get that same answer or very close to it? Okay. 8.3. Okay. I'm sure. You got 8.3. 8.3. I got 8.3. I'm going to put 8.3. If you held decimal places, it might be off just a little bit. But if you do the 29.72, then I think it does come out to 19.83. Good. Good, good, good. Okay. Then you're going to notice that the other one that we have to do the components for, TAC. TAC does not have a magnitude. So we're going to put each one of those components in terms of the variable TAC. Okay. So let's start with the TACX, okay, equal to, and you'll notice that theta is right here. So that means that theta is 69.44, and that is going to be using the cosine function because this is a side adjacent and this is our hypotenuse. So cosine of 69.44 degrees times TAC. Okay, so this one, we're just going to find the decimal equivalent of the cosine of 69.44, and then we're going to leave it in terms of that hypotenuse. I got 0.3512. Oh, it sounds like Josiah got the same thing. Shouldn't it be? It should be. You know what? It should be pounds. Thank you, Ava. TABY needs to be pounds, not degrees. Degrees is the angle. Pounds are the units. These are forces. Thank you very much. Yes, 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 Matthew. Thank you. Just saw that. Now, TACX, we're going to leave just like this. This is as far as we can go, okay, in terms of its hypotenuse. So we're going to do that very same thing for TACY. TACY is the vertical, which is going to be the equivalent on this side, which is going to be side opposite using the hypotenuse. So that is going to be the sine of 69.44 degrees times TAC, its hypotenuse. So TACY 0.936. You got one. I got three. I use this 69.44 sine. Yeah, I'm gonna stick with my number. You like I said, you might have more decimals than what I have here, and then this should be TAC. Okay. So 0.9363 or something very close. I'm not going to look if you, like I said, if you're holding more decimal places in your calculator, then it might be off just a little bit. Okay. So now that we have all of our forces on the X and Y axes, we can go ahead and use our equations of equilibrium. So step 3 is going to be equations of equilibrium. Okay. And there's two of those, right? There's some of the forces in the X equals 0 and some of the forces in the Y equals 0. I tend to, unless there's a good reason not to, I tend to use some of the forces in the X equals 0 first, all right? Just because X is before Y. So I'm going to do that. I'm going to sum my forces in the X direction equal to 0. You have to write this out. Okay, and I just want to remind you, this is an equation of equilibrium. It has an equal sign and two sides. So throughout, we need to see that. Now, on the left-hand side, representing the sum of the forces in the X. What that means is we're going to look back up here at our diagram, and we are going to look at this X-axis, and we are going to identify, in this case, the three forces that are on there. Now, on that left-hand side, we're going to assign a positive or a negative, depending if they're pointing to the left or to the right. Okay? So as we look here, starting on the right-hand side, we're going to have a positive TACX and a positive FD. And then we're going to have a negative TABX because TABX is pointing to the left. So I have a TACX positive plus FD minus TABX. This represents the sum of the forces in the X side of our equation. Okay? And now we're going to set that equal to 0. Don't forget that. I look for that. All right? If not, that's a problem. Okay? We don't want it to magically appear. Okay, so now we have our equation here. Now we're going to look, do we have values for these variables? This is called putting the equation in variable form before we put numbers in, okay? Before we put numbers in. So our TACX, that's right here. So that's going to be 0.3512 TAC. Now, FD, we don't have any values for, and it wasn't something that we derived a component for, so that's going to stay as FD. And then minus TABX, which is right here, that is 34.73 pounds. All right. And we're going to set that equal to 0. Remember, two sides here. Now, if we can combine anything, we want to do that. Or if we want to move something over to the other side, I'm actually going to move this 34.73 pounds over to the other side and keep then the two variables on the left. So I'm going to write this 0.3512 TAC plus FD is equal to, it's negative 34 on this side, so it's when it goes to the other side, it becomes positive 34.73 pounds. And this is where we have to leave it because we have two unknowns in this one equation. We can't go any further. Okay. But we've got another equation of equilibrium, don't we? So what we're going to do is we're going to go over to that other equation and we're going to see what that brings us. Okay. So I'm going to continue on with my sum of the forces in the y equals 0. Okay, sum of the forces in the y equals 0. So I'm going to bring back my diagram. Okay, I'm going to bring back my diagram. And we are going to look in the y direction only. What I want you to do is write in variable form what your equation is going to be for the y side of this equation. Okay. So go ahead and write that and then we'll compare. Give you a chance. So as we look at that sum of the forces in the y side, we're going to have a positive TACY, a positive TABY, and a negative 60 pounds. Okay, we can put that value right in there because it's along the y-axis. So don't forget that 60 pounds. So we've got a positive TACY, positive TABY, and a minus 60 pounds. And we're going to set that equal to 0. Now, we only have 3 forces along the y-axis. If there was 4, we would continue to add. If there was 1, we would just put 1. So however many forces are on that y-axis or the axis that we're summing on, and the axis that we're summing on is what we want to use. So now we want to see, are there any values for these two variables? So if we look at TACY, we have 0.9363 TAC. So I'm going to put that in place here. 0.9363 TAC. Okay. Plus TABY, which is 19.83 pounds. And then we have minus 60 pounds is equal to 0. Oh, this is good news. We've got 2 items that we can combine, and we have only 1 unknown. So we'll be able to solve for TAC over here without doing substitution. So that might be a good thing. So go ahead and combine. So I've got a 0.9363 TAC minus 40.17 pounds is equal to 0. Moving that 40.17 to the other side, 0.9363 TAC is equal to 40.17 pounds. And now solving for TAC, you get 42.9. Yeah, yep, the book gets that too. Good. Now, what's nice, like I said earlier, we didn't have 2 unknowns here. So what we get to do is we get to use this value that we got at the sum of the forces in the y and go back to the sum of the forces in the x. Now, in my case, I don't have much room down here, okay? So I'm going to pull this one forward, okay? So I'm going to kind of pull this in here. This is going to be my 0.3512 TAC plus FD, force D, is equal to 34.73 pounds. Okay. This was from the sum of the forces in the X. This is how far I could go last time, right? Now, if you have room underneath here, reasonable room underneath here that I could reasonably read, don't try to just squeeze it in to squeeze it in. If you have to, just create another line here. That's no problem. Okay. I've got to be able to follow it along. Now, what we're going to do is we're going to put our 42.19 where we see TAC. So 0.3512 times 42.9 pounds. Notice I'm putting the units in all phases of the problem. Don't you lose the units, okay? Because we want to be sure that we're combining and we have the right variables and units for things. So plus force D is equal to 34.73 pounds. We're going to multiply that out. So this is going to be 15.068 pounds plus FD is equal to 34.73 pounds. I'm going to move this to the other side. And this is going to be 19.66 pounds for our force at D. Okay. And then box around that because that's one of the two answers that we wanted to find. Okay. Did everybody get that same number, 19.66, Jaden? You got what? No, that's probably fine. That's probably fine. Yeah, reasonably within. So if you're 19.72, that's not terrible, but yeah, make sure that you're holding, 4 or 5 decimal places here all the way along. If you start rounding like this stuff where you've got 4, you're using the decimal equivalents of the sines and the cosines, make sure that you're holding those 4 or 5 decimal places because otherwise it'll make a big difference in the end. Okay, so that is our last practice problem for the set in module 3. If we kind of review the steps here, as we've been doing for each one of these, we start out with our diagram. Okay, make sure this diagram is nice and big. If you are doing this little diagram over in the corner, I'm not accepting it. All right, half the page, set it up. All right, I want you to be able to put all the labels in, all the angles, and if you are trying to squeeze it into one spot, I can't read it. Okay, and remember, part of the training that we're giving you is that you have to be able to reasonably communicate your ideas to other people. So, so taking the time when you're handing in assignments is really important. Okay. So half the page, I want to see that. And then, we got to calculate some angles. So this was our diagram. Don't forget your convention. This is at the top of each problem, not problem set, each problem. Okay. Ideally, I'd love for you to start each one of your problems on a new piece of paper. That always is just kind of nice. It's easy for me to follow. But if you have room and you want to continue on and it's reasonable, that's okay. But half piece of paper. All right. Everybody understand that? Okay. All right. Then you're going to be doing any components that are appropriate. So if you have any forces that aren't on the X and Y axis, you're going to be doing components. Then you're going to be using your 2 equations of equilibrium. Summing the forces in the X equals 0. Make sure you write out sum the forces in the X equals 0. Then on the next line, you're going to write out your equation in variable form. Notice I didn't put the numbers in here yet. I just wrote out what I had up here on my diagram, okay? And then the line below that, I put the numbers in that I have and do any combining and rearranging that I need to, okay? Also make sure that each one of these is an equation. There's an equal sign with 2 sides. Make sure you're equaling to 0 where it's appropriate, okay? And then sum the forces in the y. Again, tell me you're going to do that. Don't just start randomly writing numbers. Write your equation in variable form first. So you're looking at anything that's on the y-axis, the way you have it drawn on your diagram, okay? Equal to 0. Then you're going to put in your numbers, combine, and solve, as you're able. And then here, substituting back into the other equation. And notice that I have a box around my final answers. Each one of my finals answers has a variable. So I don't have a random number with a box around it. Okay, you're labeling what this is, and what you're labeling is what the problem was originally asking for. That's why if it's only asking for two values, what is the tension in cable AC and what is the force, the drag force that hull is going to see, I should only see two boxes. Okay, because that's answering the question. If I have 5 boxes, then you've been boxing, all these intermittent answers. Intermittent answers are clouds or underlines, okay? Just so we can call our attention to them, but boxes around final answers. I know, it sounds like, gosh, Kelly, all these rules. I have 17 people I have to correct work for. So it's really nice when I can go through and I can follow and you're doing it the way I'm asking. That's very helpful. All right. Any questions on formatting and what we're going to be handing in? Okay. So let's take a peek at our practice problems. Bless you. And if we go to the practice problems in Module 3, we now have the 3 practice problems done, okay? Remember, we're doing these all with rectangular components. Since we did the practice problems with rectangular components, we are doing our application problems with rectangular components only, okay? Even if you're like, well, I could use the cosine law. Nope. Rectangular coordinate, or I'm sorry, rectangular component method only, all right, for all of these. Just as a side note, make sure that we're looking at our files before we're uploading them. There have been a couple that were a little blurry or a little too grainy, and I couldn't read, so I couldn't give you points, okay? And then I'm asking you to resubmit. So please check those before you upload those. And I think that's it. Any questions here? Okay. All right, so what that does is that brings us to an end of the content for Module 3. We're going to be looking at a couple setups on application problems, but I'll start a new video for those.